Hello everyone, today we continue to learn the induction formula. Through the previous study, we used the symmetry of the circle and the definition of trigonometric function to derive the induction formulas 2, 3, and 4 among them. The second induction formula is about the trigonometric function relationship between pi plus alpha and alpha. The third induction formula is about the trigonometric function relationship between negative alpha and alpha. Induction formula 4 is about the trigonometric function relationship between pi minus alpha and alpha. Then, combined with formula 1 and 2, 3 and 4, we can convert the trigonometric function value of the angle in any range into the trigonometric function value of the angle in the half-closed and half-open interval from 0 to 2 pi. The application of these three sets of induction formulas is also an important means to solve the problem of trigonometric functions. Reviewing the derivation process of these three sets of induction formulas, they are all obtained by means of the symmetry of the unit circle and the corner periphery about the origin, about the x-axis, and about the y-axis. Is there any other special symmetry in the unit circle? Do the trigonometric functions of their corresponding angles also have some special relations? Today we will continue to explore the induction formula. Think about it. How did we deduce the induction formulas 2, 3, and 4 last time? We got it from the symmetry of the point on the unit circle about the origin coordinate axis. What connections do we make to the angles before and after symmetry? First, we determine the quantitative relationship between the front and rear angles of symmetry, such as OP1 and OP2, whose terminal edge is symmetrical about the origin. Their angles can be expressed as alpha and pi minus alpha. Then we determine the coordinate relationship between the intersection of the front and rear end edges of symmetry and the unit circle. For example, the coordinates of point P1 are x and y. After it is symmetrical about the origin, the coordinates of point G2 are negative x and negative y. Finally, we define it according to the trigonometric function and integrate the previous isometric relationship to get the final trigonometric function relationship. For example, sine pi plus alpha equals negative sine alpha, and cosine pi plus alpha equals negative cosine alpha. Tangent pi plus alpha equals tangent alpha. After step-by-step reasoning, we get the induction formulas 2, 3, and 4. So today we will change the axis of symmetry into a straight line y equals x, and then use its symmetry to see if we can explore a new induction formula. In order to deduce a new formula, let's first consider question 1. Question 1. What is the relationship between the angle gamma with OP5 as the terminal edge and the angle alpha with OP1 as the terminal edge when P1 is about the symmetrical point P5 where the straight line y is equal to x? From this figure, we can see that since point P1 and point P5 are symmetrical with respect to the outside of the straight line, the angle between OP5 and the y-axis and the angle between OP1 and the x-axis are equal, both equal to alpha. So we can get the quantitative relationship that gamma is equal to half of pi minus alpha. When point P1 is not in the first quadrant, is the quantitative relationship that gamma is equal to 2 of pi minus alpha still true? You can draw a few more images to try. Here we present P1 in different quadrants and 4 images. Point P1 is in the first quadrant, point P1 is in the second quadrant, point P1 is in the third quadrant, and point P1 is in the fourth quadrant, and its position about the point P5 where the line y equals x symmetry. In fact, no matter where P1 is, because point P1 and point P5 are symmetrical about line y equals x, the angle from OP1 to line y equals x and the angle from OP5 to line y equals x are always equal. We can remember that this isometric is theta. In this way, the angle alpha with OP1 as the terminal edge can be expressed as alpha equal to a quarter of pi plus theta. The angle gamma with OP1 as the terminal edge can be expressed as a quarter of pi minus theta. Next, we can add the two equations and eliminate theta. We get the quantitative relationship that alpha plus gamma is equal to 2 parts of pi. After further sorting, gamma is equal to half of pi minus alpha. This shows that no matter what quadrant or coordinate axis point P1 is in, we can always have the angular alpha with respect to the symmetrical angle gamma equal to x outside the straight line, and there is always a quantitative relationship between gamma equal to half pi minus alpha. Next, let's consider question 2. Is there any relationship between the coordinates of 2 points symmetrical about the straight line y equal to x in the rectangular coordinate system? In order to get the coordinate relationship, we can do the vertical section of the x-axis through point P1, go through point P5 and make the vertical section of y-axis. Since P1 and P5 are symmetrical with respect to the straight line y, we can easily prove that the two triangles after the vertical line segment are congruent. If the corresponding sides of a congruent triangle are equal, we can convert the length of the corresponding sides into a coordinate relationship, and then we can get the quantitative relationship that x5 is equal to y1 and y5 is equal to x1. When point P falls on other quadrants or coordinate axes, this coordinate relationship still holds. You can try to prove it after class. Next, we should solve problem 3. What is the relationship between the trigonometric function value of the angle alpha whose terminal edge is OP and the angle gamma whose terminal edge is OP5? According to the definition of trigonometric function, we can integrate the previous isometric relationship to get sine gamma is equal to sine half pi minus alpha. By definition, it is equal to y5 and x1, so it is equal to cosine alpha. Cosine gamma is equal to cosine half pi minus alpha. By definition, it is equal to x5, which is equal to y1. Finally, it is equal to sine alpha. So we get the fifth set of induction formulas. The angle at which the terminal edge is symmetrical with respect to y equal to x. I don't have sine half pi minus alpha, which equals cosine alpha. Cosine half pi minus alpha equals sine alpha. Next, let's look at this set of formulas. Sine half pi plus alpha equals cosine alpha, and cosine half pi plus alpha equals negative sine alpha. Can you reasonably use the symmetry relationship to derive this set of formulas? First of all, we need to solve the symmetric relationship between the terminal edge of angle to pi plus alpha and the terminal edge up 1 of angle alpha. To solve this problem, we can first make point P a symmetrical point P5 with respect to the line y equal to x. Then make point P5 point P6 symmetrical about the y-axis. Then OP6 is the final edge of pi plus alpha. Next we will study the coordinate problem. The coordinates of P1 point are x1 and y1. From the previous knowledge, we can get that the coordinates of point P5 are y1 and x1. After y-axis symmetry, the coordinates of P6 point are negative y1, x1. Therefore, the abscissa x6 of point P6 is equal to negative y1, and the ordinate y6 of point P6 is equal to x1. Next, combined with the definition of trigonometric function and integrating the previous isometric relationship, we can get the sixth group of induction formulas. In this way, we have derived the induction formula 5. Half of pi minus alpha of sine equals cosine alpha, and half of pi minus alpha of cosine equals sine alpha, and induction formula 6. Sine half pi plus alpha equals cosine alpha, and cosine half pi plus alpha equals negative sine alpha. The fifth set of formulas is the functional relationship between half pi minus alpha and angle alpha. The sixth group of induction formulas is the function of half pi plus alpha and alpha. The characteristic of these formulas is that the function names around the equal sign have changed. That is, the right side of the equal sign becomes the conamed trigonometric function of the alpha angle. The symbol on the right side of the formula is the symbol of the trigonometric function value when alpha is taken as an acute angle. We have learned 6 sets of induction formulas. Will you use these 6 sets of induction formulas to solve the problem? Next, let's look at example 1. For example 1, prove that 3 pi over 2 minus alpha is equal to negative cosine alpha. Second, cosine 3 pi over 2 plus alpha equals sine alpha. Let's prove the first topic first. We can sort sine 3 pi over 2 minus alpha into the sum of sine pi plus half pi minus alpha. Then the half pi minus alpha is regarded as a whole and can be simplified into the form of negative sine half pi minus alpha by using the induction formula 2. Since sine half pi minus alpha, it can be obtained that it is equal to cosine alpha by using the induction formula. So negative sine half pi minus alpha is equal to negative cosine alpha. We have proved the first question. Second topic, we can put cosine 3 pi over 2 plus alpha into the sum of cosine pi plus half pi plus alpha, and then take half pi plus alpha as a whole. Using the induction formula 2, it is reduced to negative cosine half pi plus alpha, where half of the cosine pi plus alpha is equal to negative sine alpha using the induction formula 6. So negative cosine half pi plus alpha equals sine alpha. Next, let's take a look at example 2, simplifying evaluation. How should we handle such a complex equation? If we directly substitute alpha equal to -1/3 pi into each part of the equation to calculate, then you can imagine that the computational complexity is too high. So can we use the induction formula to turn each part of the equation into a trigonometric function of angle alpha? After sorting, we will then substitute alpha equal to -1/3 pi into the calculation. It can play a role in simplifying complexity. Okay, using the induction formula, we first simplify the first part of the denominator, sine -pi minus alpha, to negative sine pi plus 2. Then, we organize the second part of the denominator, sine 9 pi over 2 plus alpha, into the sum of 4 pi plus half pi plus alpha, in preparation for induction formula 1. The molecule cosine is divided into two parts pi and alpha, and is directly simplified into negative sine alpha using induction formula 6. Cosine 11 pi over 2 minus alpha, we can organize it into the sum of cosine 5 pi plus half pi minus alpha. Next, further processing will be performed on the equation. The molecule negative sine pi plus alpha can be simplified into sine alpha using induction formula 2. 4 sine pi's plus half of the pi plus alpha can be obtained using induction formula 1, which is sine half pi plus alpha. We do not need to do any processing for negative sine alpha. Cosine 5 pi plus half pi minus alpha. We consider half pi minus alpha as a whole, and after simplification, we obtain it as negative cosine half pi minus alpha. For the denominator sine half pi plus alpha, we use induction formula 6, which is cosine alpha. The cosine of the molecule is divided by half pi minus alpha, and using induction formula 5, it becomes sine alpha. So in the end, we can simplify it into the form of cosine alpha divided by sine alpha. The final result is tank alpha. When alpha is equal to -1/3 of pi, the original equation is equal to tangent -1/3 of pi, and equal to negative tangent 1/3 of pi, it is equal to -√3. As you can see, using the induction formula, first transform each part of the equation into a trigonometric function with an alpha angle. Its advantages are very obvious. So in the future, we will first simplify the induction formula and then solve the trigonometric function problem, which is a commonly used method. That's all for today's class. Goodbye, everyone.